Hello and welcome to a video on analytical chemistry. So in this video we're going to be going through the combined and triple content. There will be another video that has just the triple only content. So we're going to talk about pure substances and formulations, chromatography, and the different tests for gases. So let's start off with pure substances. So the key part about pure substances is you would have touched upon it a lot especially during key stage 3, so that'd be year 7, 8, potentially 9. And the key part you need to take away is that a pure substance has a very specific boiling point and melting point. So a specific boiling point, I'll put that shorthand, / melting point. Now we can use a graph to display this, and you will often see this in exams. So this will be energy, and this will be time. And as it's going along, we're heating up a substance, we're heating it up, and if it's a pure substance, it will flatline as we change state. And that's linking to the boiling point and melting point. That flat line there indicates a pure substance. Now, if it went a bit like this, that would be an impure substance because it has a range of melting points and boiling points. So the key part you need to take away is that the specific boiling point is this flat line here, okay? And this is where it changes state, whether that's from a solid to a liquid or a liquid to a gas. It doesn't matter, it just means that this flat line, because it's got a specific boiling point and melting point. And you will get asked that in exams. You'll see this sort of graph and you'll have to choose which is the pure substance and which is an impure substance using this. Right, let's move on to formulations. So a formulation is a mixture designed as a useful product. So a good example you could think of is paint. Paint has lots of different factors in it, and it's important that each part is measured out in careful quantity. So carefully measured quantities. And that's important because if you get one of the quantities slightly wrong, it might not work properly. So let's say you're making a medicine and you get certain medicines which have caffeine in. Now, caffeine helps to speed up the medicine getting to the place that needs to be. Let's say it's a painkiller, we got aspirin or paracetamol, ibuprofen. You put a bit of caffeine with it, it can speed up. You put too much caffeine in, you might not have enough painkiller in there, therefore it might not work. So you need it to be carefully measured out. Now, some good examples are fuels, so petrol, it's not just pure, there's a lot of other things in there, paint, medicine, as we're just talking about, and foods. The most common one, which some of you might have heard of, is being named after formulation, is baby formula. Baby formula is a mix of lots of different things, and they have to get it spot on to ensure that the baby is getting health focused food. Okay, so you will have to identify formulations from appropriate data, and that will be things like a breakdown of the chemicals involved or the materials in it, but you have some questions that will help you to understand them. Right, let's move on to chromatography. So let's go for another color. We'll go for blue for this bit. Chromatography. Now you will hopefully have all done some paper chromatography, but we're going to take it a little bit further and we're going to add some maths to it. It's not complex maths, but it's still important maths. So we use chromatography to separate mixtures, plus help us identify substances. So these are the uses of it. So you might have done where you found the culprit of a crime because they used a pen and we could figure that out, or you might have just separated pen inks out, which is perfect. Now, you need to understand two bits of terminology. We have stationary phase and we have mobile phase. Now, this sounds complex, but in actual fact, it's quite straightforward. So the stationary phase is the solid part. It's a solid part. And the mobile phase is the liquid. So for paper chromatography, the one that you will have focused on mostly, you'll have, this will be the water at bottom of beaker. Now it's the mobile phase because it moves, it flows through the stationary part, which is the paper that hangs into the water. So this is the mobile, it flows through. This is the stationary phase, it is the paper that you put the ink dot onto. Okay, so that's the key part. Now it sounds complex, but just remember, stationary phase is the solid, mobile phase is the bit that moves, therefore it's the liquid because it flows through the paper. Right, now I'm going to draw it out and then we can look at the maths behind it. That should help you understand a little bit more. So let's say we've got a beaker here. We have our mobile phase, the bit of water at the bottom. And we have our stationary phase, the paper that just touches the water. Remember, we've got the line along it, and we have, I'll get a colour for this, let's go for it. Okay, so that will be our ink dot. Now, what will happen is the mobile phase will move up, it will flow through the stationary phase, and it will carry the ink. Now, the mobile phase should travel all the way to the top. So it should travel all the way up here. Mobile phase end point. Now, the stationary phase will stay still, but we are caring about how far the ink dot moves. Let's say the ink dot moves up to here. So this is another important part that we need. So this is the substance end point. We could change this mobile phase endpoint. We could also call it, this is where it just gets a bit confusing, but we'll just call it the solvent endpoint. Because the solvent is the liquid at the bottom, so this is where it ends up. So these are your two parts. Now what you'll have to do is you'll be measuring the distance that they have travelled. So we will measure from this line here, because that's where the ink starts, so we don't want to measure the mobile phase starting below it. So we measure the difference from here to here to get the solvent distance, and we measure from here to here to get the substance distance. Therefore, we can get what we call an RF value. So the RF, sorry, that should be a capital R. The RF value is equal to the substance distance divided by the solvent distance. So we take this number, the substance distance, and we put it on top. We take the solvent distance and we put it on the bottom. We do the maths, dividing it, and we'll end up with a number between 0 and 1. You cannot go higher than 1, and you cannot go below 0. If you have got a number that's outside of this, 0 to 1, you have got it wrong. So 0 means the substance is insoluble. It hasn't moved at all. It stayed exactly there. So it's insoluble because it's not being dissolved by the mobile phase, the solvent. 1, we'll call it super soluble. It's completely dissolved into it. It's moved with the mobile phase. It's basically become part of the mobile or solvent part of chromatography. So it's not a complex bit of maths. You just have to remember that what you need to measure, you measure from the line either to the top of the mobile phase to get the solvent distance, or to the top of here to get the substance distance. Then you can put it into the equation and you'll get a number between 0 and 1. 0 being insoluble, 1 being super soluble. Right, let's move on to the final bit of this video, and that is the test for gases. So we'll go for green for the test for gases. We have 3 different gases we need to know. Oxygen. To test for oxygen, you will relight a glowing splint. So what you'll do is you'll have a glowing splint that you've just blown out. You'll put it into a test tube that contains what you think is oxygen, and it will reignite and go back on fire. And that is because oxygen is one of the parts you need for fire to occur. It's one of the fire triangle. So you give it a massive amount of oxygen, you'll relight a glowing splint. CO2. This test is lime water, which is calcium hydroxide. Calcium hydroxide, what you'll do is you'll bubble some carbon dioxide through lime water. If it goes cloudy, you've got CO2. If it stays clear, no CO2. So CO2 makes lime water cloudy. And finally, chlorine. You use damp litmus paper. If you have chlorine present, the damp litmus paper will be bleached. It will go white. If you have a white bit of litmus paper at the end, you know there is chlorine present. So, oxygen relights a glowing splint. Carbon dioxide, lime water, will go cloudy once carbon dioxide is bubbled through, and chlorine, damp litmus paper, will go white. Right, that is the first part of the analytical chemistry topic, and it is the only part for the combined students. Thank you very much for watching.